Have you ever just, stopped and thought about your heart? It's this incredible machine, just humming along, beating more than 100,000 times a day, every single day, without you ever having to think about it. But what's really wild is that it does all this completely on its own. It doesn't wait for a command from your brain. So that's what we're going to dig into, this amazing self-sufficient power that's sitting right inside your chest. And that really is the big question, isn't it? How does it do that? How does this one organ manage to create its own rhythm, its own life-giving pulse, second after second without fail? Well, the answer is this beautiful and, kind of complex electrical symphony that's playing out inside you right now. So it all has to start somewhere. And for the heart, everything, and I mean everything, begins with a single tiny spark. See, the heart doesn't wait for permission. It makes its own electricity. This is the absolute first, most fundamental thing you have to know about it, and it's what makes it so special. This incredible ability has a name. It's called automatism. You can think of it as the heart's own little superpower, the power to just spontaneously create an electrical impulse out of thin air. Now, it's not just happening randomly. It all kicks off in one very specific spot, a little cluster of cells called the sinus node. This is the heart's natural pacemaker, the conductor of the orchestra, the one that creates that very first spark. Okay, so once that spark is born, it can't just hang out. It's got a message to deliver, and it needs to get that message to the entire heart, and fast. So let's follow that spark on its incredible high-speed journey. This journey basically happens in a few key steps. We've got the creation, right? That's automatism. Then that spark has to travel. Once it gets to its destination, it causes activation. That activation leads to the main event, the action, which is the big squeeze. And all the while, the heart has to maintain its form. All right, so let's walk through what each of these really means. First up, after the spark is made, is conductivity. You should think of this like the heart's own internal high-speed internet, or maybe a super efficient highway system. It's this special wiring that makes sure the electrical impulse gets from that starting point, the sinus node, to every single muscle cell in a perfectly timed, coordinated way. Next, excitability. This is the moment the signal actually lands. When that electrical impulse arrives at a heart muscle cell, the cell gets excited or activated. It's like flipping a switch. This creates a wave of electrical energy sweeping across the heart, and that electrical signature is precisely what an ECG machine is built to listen to and draw out for us. Now, all this electrical stuff, the spark, the travel, the excitement, it's all for one reason. It's to get to the action, and that action is contractility. This is the payoff. In response to getting that electrical jolt, the heart muscle physically contracts. It squeezes. An electrical signal is literally turned into a powerful mechanical pump that moves your blood. It's amazing. And finally, there's tonicity. Now, this one's a little different. It's not really part of the active journey of the spark. It's more about the heart's baseline state, its ability to just hold its shape, to stay firm and ready, especially when it's relaxing and refilling with blood. It's the structural integrity that makes all the action possible. So the heart creates a spark, it travels, it activates the muscle, and you get a pump. But think about it. For this system to work over and over without becoming a total mess, there has to be a pause, a mandatory cool-down period after every single beat. This built-in safety mechanism is called refractoriness. It's super important. Right after a heart cell fires, it enters this brief timeout where it absolutely cannot respond to another signal. The best analogy is an old camera flash. You take a picture, the flash goes off, and then you have to wait a second for it to recharge before it can flash again. Same idea. It's the one rule that keeps the whole system from descending into chaos. And it's not just one simple cooldown. It actually happens in two phases. First, there's the absolute refractory period. During this time, the cell is completely offline. It doesn't matter how strong a new signal is, it will not fire. But that's followed by the relative refractory period. Here, the cell is kind of vulnerable. It can be triggered again, but it takes a much stronger than usual spark to do it. And here's where it all gets really cool. This whole invisible process, this cooldown, is something we can actually see. It shows up right on the ECG. That absolute no-go period, that corresponds perfectly to what doctors see as the QRS complex and the ST segment. And that vulnerable, maybe I'll fire relative period, that's the T wave. It's all right there. So this system is almost perfect. The timing is exquisite. But what happens when that timing gets thrown off? What if a stray spark shows up early, when a part of the heart is still in its cooldown? Well, that's when you get something called aberrancy. It basically means an impulse took a weird path. So imagine a spark fires off too soon. It starts traveling down the heart's normal wiring, but it finds one of the pathways is still in that refractory cooldown mode. It's blocked. So the signal is forced to take a slow, inefficient detour. That creates an abnormal heartbeat. Okay, wow. So we've gone from the birth of a single spark all the way to what happens when things go a little wrong. Let's pull all these threads together now and look at what this means for how we actually read the heart's story. This all comes home to roost with the electrocardiogram, the ECG. It is the absolute perfect tool for seeing this electrical story play out. Pretty much everything we've talked about, the spark's creation, its travel speed, the activation, that critical cooldown, even when a signal goes astray with aberrancy, all of that is visible on an ECG. But it's really important to know what it can't tell us. While a weird ECG might suggest there's a problem with the pumping strength, with contractility, it can't directly measure that physical force. And it tells us absolutely nothing about the heart's physical shape, its tonicity. So in the end, the ECG gives us this incredibly detailed, second-by-second story of the heart's electrical life. But that brings up one last really fascinating question. What happens when the problem isn't the spark or the wiring? What happens when the electricity is perfect, but the muscle, the pump itself, is what's failing? Well, that's a whole different story.